Chapter 7, Section 3, Trigonometric Substitution. I'm your host, Dr. D. Okay, here we go. Now, most of the substitutions we've done before have been u equals a function of x. This time, we're going the other direction. We're going x is a function of theta. So instead of u equaling something with x in it, we have x equals something with theta in it. Now, if your integrand contains the square root of a squared minus x squared, then you're going to use x equals a sine theta, because we know that cosine squared equals 1 minus sine squared. So you're going to end up with an a squared minus an a squared sine squared theta, which will end up being an a squared cosine squared theta under the radical, and that becomes just a cosine theta outside the radical, and then we can integrate it very easily. If you have, instead of a squared minus x squared, you have a squared plus x squared under the radical, then you're going to use x equals a tangent theta, because you want to take advantage of this trigonometric substitution. And if you have x squared minus a squared under the radical, then you're going to go x equals a secant theta, because you want secant squared minus 1 equals tangent squared. You're going to have tangent squared under the radical, and that makes tangent outside. Easy to integrate. So these are all based on these two Pythagorean identities that you know and love. Now, do you think that you should actually memorize these? I think probably that would be a good idea.
That's the smartest thing I've ever heard anyone say about anything.
Yes. Okay, so we're going to memorize these. Now, today's lesson, what I'm going to do is I'm going to give you one example problem of each one of these types. We're going to compute them and get our final answer. We'll have a couple with indefinite integrals and a couple with definite integrals. Then we'll do a warning problem. A problem that most people go the wrong direction with, and I want to make sure that you know not to do that, because on the AP exam, they're going to try to trick you into doing that. So, we won't get tricked. And the fifth problem we're going to do is maximum juice. So, that's it. Let's get started. Okay, so we have the integral of the square root of 9 minus x squared over x squared dx. And just like we said, if we have an a squared minus x squared, we have 9 minus x squared. That means a is 9, or a squared is 9, so a is 3. So we want x equals 3 sine theta. Well, let's do that then. So x equals 3 sine theta. Well, notice we not only have an x, but we have a dx too. Well, let's just take care of the dx right away. So that means dx equals 3 cosine theta d theta. And I'm going to need that piece. Now, let's go back to our x. So if x is 3 sine theta, then what's under my radical is going to be the square root of 9 minus x squared becomes the square root of 9 minus 9 sine squared theta. Okay, now that becomes, we factor a 9 out of this whole thing, so it becomes 9 times the quantity 1 minus sine squared theta. And 1 minus sine squared theta, cosine squared theta. Then, square root of 9 cosine squared theta is 3 cosine theta. Now, the one other piece we have is x squared here. So x squared equals 9 sine squared theta. All right, now we're ready to apply all of our trig substitutions. So I have the integral of the square root, well, the radical turns out to be a 3 cosine theta, over the x squared, which is a 9 sine squared theta, dx, which turns out to equal 3 cosine theta d theta. Okay, so let's put all this together then. On top I've got 3 times 3 is 9, cosine times cosine is cosine squared theta. Yeah, let's just do it like this. Over 9 sine squared theta d theta. Well, 9 over 9 is 1, and cosine squared over sine squared is cotangent squared. So, notice what just happened. When we did our trig substitution, we now have a trig integral to perform. So, when you finish the setup of section 3, you have section 2. And we just did that. It's like your little brother could do that. Okay, so the integral of cotangent squared theta d theta. Well, what are we going to do with that? Well, we know that cosecant squared, rats. Yeah, let's just do that over. We'll edit that out. We know that cosecant squared theta minus cotangent squared theta equals 1. Now, cotangent squared theta then equals cosecant squared minus 1. So, I'm going to make that substitution then. So I've got the integral of cosecant squared theta minus 1 d theta. Well, now I'm ready for the integration, because I know that the integral of secant squared is tangent, because derivative of tangent is secant squared. The derivative, or the integral of cosecant squared, is negative cotangent. So this becomes negative cotangent theta. Now the minus 1 becomes a minus theta plus c. Now, just like when we did a u substitution, we need to get our x's back. Well, we have to do the same thing here. So we need to get x's back, knowing that x is 3 sine theta, and we have a cotangent theta. So what we're going to do is we're going to use a right triangle to help us out with this. So the right triangle, see, I know that x equals 3 sine theta. And that means that sine theta equals x over 3. Well, that means if this angle is theta, then opposite has to be x, and the hypotenuse has to be 3. So what does that make my adjacent side? The adjacent side is 9 minus x squared under the radical. Now, if I square the bottom, I get 9 minus x squared. Square the right side, I get x squared. 9 minus x squared plus x squared is 9. That works. All right, so now I have negative cotangent theta. Well, what is cotangent? It's adjacent over opposite. So this becomes negative square root of 9 minus x squared over x. Negative opposite, or adjacent over opposite. There's my cotangent. Now, I've got my theta. What's theta equal? Well, it's the simplest way to explain theta is if sine theta is x over 3, then theta is the inverse sine of x over 3. That's it, game over. Okay, so let's just check to make sure that the book actually agrees with us. Yeah, it does. Okay, that's happy. All right, let's try another example. This time, we have an a squared plus x squared. So we can't use the sine, we have to use the tangent. So what we say is, let x equal 2 tangent theta. Because notice, a squared is 4, so a is 2. Okay, so now, if x is 2 tangent theta, we need a dx. So dx, derivative of tangent, secant squared. Okay, then we need an x squared. So x squared equals 4 tangent squared theta. Now last, we'll do the radical. So the square root of x squared plus 4 is going to equal the square root of, now we're going to put our 2 tangent theta in for x, so we get a 4 tangent squared theta plus 1, and, oh, I'm sorry, not plus 1, but plus 4. Now we factor a 4 out, so we have the square root of 4 times the coordinate tangent squared theta plus 1. And so the tangent squared theta plus 1 becomes secant squared theta. Because secant squared minus tangent squared is 1, so that means secant squared equals tangent squared plus 1. And finally, we take the square root, so we end up with 2 secant theta. All right, so once again, we've completed all of our trig substitutions for each piece here in this integral. So my integral is going to become the integral of 1 over x squared, which is 4 tangent squared theta, times the radical times the dx, so we'll just put our dx up on top. So that becomes 2 secant squared theta d theta. All right, now let's clean this up. So notice the 2's cancel, and I'm left with just 1/4 times the integral of, now, 1 secant cancels, so we're left with secant theta d theta over tangent squared theta. Okay, now let's see. You know what, I would say the easiest thing to do here is put everything in sine and cosine. So notice this becomes 1/4. Now, secant is 1 over cosine, so I can just put the cosine theta on the bottom. And tangent squared is sine squared over cosine, so I'm going to put a, let's see, tangent squared on the bottom means sine squared over cosine squared on the bottom. So when I flip that, it's going to end up being cosine squared over sine squared. So notice tangent squared is on the bottom, so that means cotangent squared would be on the top, and there's cotangent squared right there. And now we have our d theta. Okay, so now clearly the cosine cancels, and I'm left with 1/4 times integral of cosine theta d theta over sine squared theta. All right, now, if we go u equals cosine theta d theta, then du is negative . Let's see, now u is sine squared theta, du would be might be able to do a u substitution. Let's see. Yeah, okay, that's what I was thinking we should do. All right, so what we're going to do is let u equal sine squared theta. Now, that means du is going to be the derivative of sine squared, which is going to be 2 sine theta times the derivative of the inside. Remember, I've got sine squared theta is really sine theta squared. So when I take the derivative of that, it's going to end up being 2 sine theta times derivative of the inside, which is cosine theta. Okay, so du is 2 sine theta cosine theta d theta. Now, wrong. cut, take two. We didn't want to do that. We could have done that, but that would lead to a mess. So, we'll edit that out. Okay, so what we're going to say is u equals sine theta, and then du is cosine theta d theta. Now I have my cosine theta d theta, and I'm all set. So then I'm going to go, this integral equals 1/4 times the integral. Cosine theta d theta becomes a du, and sine squared theta becomes u squared. That's it. Now it's an easy integral. So this becomes, well, let's just do it like this. It's 1/4 integral of u to the negative 2 du, which equals 1/4 u to the negative 1 over negative 1 plus c. So this equals negative 1 over 4u plus c. Now, what we need to do is put our thetas back. So we put theta back in here, so I've got negative 1 over 4 sine theta. Plus c, of course. Now, I need to get the x's back. So, what I do is I go with my triangle. If x is 2 tangent theta, here's theta, and x is 2 tangent theta means tangent theta equals x over 2, which means I put x over 2 opposite over adjacent. Good thing we remember our trig functions. Okay, now what's our hypotenuse? It's going to be x squared plus 2 squared. So x squared plus 4 is our hypotenuse. Oh, the square root of x squared plus 4. Okay, now I'm ready to substitute back in the x's, and I have 4 sine theta. Well, sine theta is opposite over hypotenuse. So it's negative 1 over 4 times opposite over hypotenuse. Plus c, of course. Okay, so now we're going to flip the bottom and multiply. And so we have negative square root of x squared plus 4 over 4x plus c. That's it. Game over. Now let's make sure the book agreed with us. Wait. Yeah, okay. The book agrees with us. Everything is happy. Okay, so notice this time we went from x's to thetas, and don't forget, you have to convert everything to thetas. You got to get the radical, the x squared, and the dx. Then we get down to the point where we need to go to u substitution. So now we're working with u's, and then we need to go back to the thetas, and then back to the x's, and then we're at our final answer. Okay, cruising onward. All have a definite integral, and we've got the x squared minus a squared. So this time, we're going to let x equal secant theta. And notice it's a 1, so it's a secant theta will be 1 times secant theta. So, we let x equal secant theta, and that means dx equals the derivative of secant theta, which is secant theta tangent theta, d theta, and the square root we're having a malfunction. There we are, we're back. Okay, so the square root, oh, that's obnoxious. The square root of x squared minus 1 equals the square root of secant squared theta minus 1, which equals the square root of tangent squared theta, which equals tangent theta. Now I always want to go over in my mind, secant squared minus tangent squared equals 1, and that means secant squared minus 1 equals tangent squared, and so that's correct. Okay, so notice we have dx, we have the radical. That's it. Now, one more thing. Notice x's, or the limits of integration, are in x. So we're going from x equals 2 to x equals 3. Now, if x equals 2, then we know that secant theta equals 2. And so the theta that we're using is going to be the inverse secant of 2. Or let's do it like this. Secant theta is 2, and that means that cosine theta equals a half. And so theta is the inverse cosine of 1/2, which we know is pi over 3. Now, if x is 3, the top limit of integration, then secant theta is 3, so cosine theta is 1/3. And so if cosine theta is 1/3, then theta becomes the inverse cosine of 1/3. And we'll just leave it like that because we don't have an exact angle for that. Now notice, I made, this doesn't have limits of integration in your book, so I just made that up so it didn't turn out even, but big deal. We don't mind. Okay, so now we substitute everything in. And I mean everything including the limits of integration. So we've got the integral from theta equals pi over 3 to theta equals inverse cosine 1/3 of dx, which is secant theta tangent theta d theta over the radical, which is tangent theta. Okay, so this is going to turn out nice and neat. The tangents cancel, and you're left with the integral from pi over 3 to inverse cosine of 1/3 times secant theta, secant theta d theta. Okay, now, the integral of secant theta is, you guys memorized this already, natural log of secant theta plus tangent theta. Oh, and we don't need plus c. What the heck was I thinking? Because it's a definite integral, and we're going from pi over 3 to inverse cosine 1/3. Okay, now, this is going to equal natural log of, now, we have the secant of the inverse cosine of 1/3. Secant of inverse cosine of 1/3. Well, secant and cosine are reciprocals of each other. So that means we've got the, well, one way we could do it is just make our fraction if cosine, the inverse cosine of 1/3 is the angle whose cosine function is 1/3. So it's that angle there. Ah, rats. It's this angle, where cosine is 1/3. Now, if we want the secant of that, that's going to be just 3 over 1, the reciprocal of cosine. So this thing becomes the secant of inverse cosine, ends up being 3. Plus, now let's get rid of this, plus tangent of inverse cosine 1/3. All right, yeah, we did need this back again, only I'm going to make it a little bit better. Okay, so here's 1/3. There's my cosine. Now, what's the hypotenuse? Well, 9 minus 1 is 8. So, here's my theta. So this is my theta, inverse cosine of 1/3. What's tangent of that? Square root of 8 over 1. So this becomes 3 plus square root of 8 minus, now we put pi over 3 in. So what is secant pi over 3? Well, we knew that cosine pi over 3 is 1/2, so secant pi over 3 is 2. And what's tangent pi over 3? Well, we'll just use this triangle right here. If this is pi over 3, then we know that the short side is 1, the long side is square root of 3, and the hypotenuse is 2. So tangent would be square root of 3 over 1. Okay, now that's it. I've got natural log. Now notice this already is positive, so we don't need absolute values. So I've got 3 minus 2, which is 1. Then plus the square root of 8 minus the square root of 3. Bam, that's it, game over. Now, you could plug that into your calculator and get a decimal approximation. But this is the exact answer. So, notice also, since we had limits of integration, we switched the limits of integration to thetas. Once we have that, we don't have to go back to x's again. We could go straight to the values right here. Now, if we wanted to, we could convert back to x's and we'd end up with the same thing. But that's it. All right. Okay, now, what's our trig substitution here? Well, it's x squared plus 4. So x squared plus 4 means we should go x equals 2 tangent theta, right? Right? No! Okay, watch what happens. What's much easier, oh, I forgot one key thing here. Okay, you could do this as a trig substitution, and a lot of people try that. And that's like hacking your way through the jungle with a machete, and all it takes is one little screw up and the panther jumps down from the tree onto you and eats your face. Eats your face? That was the wrong one. Eats your face? Yeah, that was what I wanted. Okay, so we don't want a trig substitution here. We want a u substitution, much simpler. So all you do is go, let u, I forgot the word let u equal x squared plus 4. So du equals 2x dx. So x dx equals 1/2 du. And then we have our x dx becomes 1/2 du. And on the bottom we have the square root of x squared plus 4, which is just the square root of u. Okay, so that equals 1/2 integral of u to the negative 1/2 du, which equals 1/2 times u to the positive 1/2 over 2. I'm sorry. Over 1/2, I mean. Plus c, senor, which is going to equal the 1/2s cancel, and you're left with the square root of u plus c. Now, we already know what u is, x squared plus 4. So that means our final integration is the square root of x squared plus 4 plus c. So, do not get sucked into a trig substitution when all you need is a u substitution. Now, if we go back through the problems that we had before, notice we can't do a u substitution here because I would need an x dx to do that. I don't have it. We can't do a u substitution here because, once again, I need an x dx and I have a dx over x squared. We can't do a u substitution here because I need an x dx again, and I only have a dx. But on this one, we do have the x dx that we need, so we just do the u substitution. Comes out really easy. Okay, so let's just see. Yeah, the book even agreed. All right, now, one last problem, and it's time for maximum juice. That's more like it. Okay, so on this one, we don't have a simple a squared minus x squared. So we have to create one. So what we're going to do is we're going to complete the square on this thing. So what we'll do then is say, the 3 minus 2x minus x squared is going to equal negative x squared plus 2x minus 3. Now, that equals negative x squared plus 2x plus, now if I want to complete the square, cut the middle term in half and square it, becomes plus 1. But now I have the minus 3 here, so this actually just becomes a minus 4 because I just added 1, so to keep it even I need to subtract 1. So now it becomes a negative, factor this, becomes an x plus 1 quantity squared minus 4. Now remember, when you have a negative out in front of a subtraction, you can just flip the subtraction.
Hey, let's do that play right now.
Okay, so this thing then becomes, what the heck am I doing? Just flip the subtraction. Yeah. Flip the subtraction and get rid of the negative. So this becomes 4 minus x plus 1 quantity squared. See, we flipped the subtraction, changed the sign outside there. Now we have it 4 minus x plus 1 quantity squared. So what we're going to do then is we're going to say let u equal x plus 1. So if u equals x plus 1, then we have du equals dx. But we also have the 3 minus 2x minus x squared equals 4 minus u. Okay. Oh no, I'm not 4 minus u, 4 minus u squared. Since 4 minus x plus 1 quantity squared is what that equals, we've got 4 minus u squared. Okay, now this makes our whole integral. The integral of x, which remember x is, oh, I didn't put x. X equals u minus 1. And dx equals du, so I can put the du out there. And what's under the radical becomes the square root of 4 minus u squared. All right, now, there's two ways of doing this. And the way I thought at first to do it was to break this up into two separate integrals. So we go equals integral of u over square root of 4 minus u squared du minus the integral of 1 over square root of 4 minus u squared du. Now notice this one you could do with a u substitution. Because if you let u equal, well, you let let v equal 4 minus u squared, then you'd have dv equals negative 2u du, and there's your u du right there. This one you need a trig substitution. But the other way to do it is to just do the trig substitution with this whole thing. And that way actually ends up turning out easier. So we'll just put this in a little box. We could do that, but we don't have to. So now what we're going to do is